Okay. 16. We're going to do 16.1, 16.2. Definition. The double integral of a region R of f x y dA is equal to the limit. Change goes to 0 on the sum of k is 1 to n for your f of xk stars and yk star with respect to the delta ak. Okay, there you go. It's a double integral. Hi, Chelsea. Theorem. This is going to be Fubini. I love that name. Imagine you wake up one day and you're Fubini's mom and you just say, what? Cook up a name for my kid. Fubini. It's awesome. You know, I have an Italian brother-in-law now, so I should convince him if he knows it. If he knows what's good for him, he'll name one of his kids Fubini. Because then that'll be the kid that I teach Calc 3 from basically birth. So the double integral on rectangular region. Rectangular regions. So this is kind of what we talked about yesterday. Oh, speaking of, okay, so I'll talk about it after this. Let f be continuous on R, and R is going to be a region of points x, y, such that A less than x is less than or equal to B, so we're bounding x, and we're going to bound y in a similar way. C less than or equal to y less than or equal to B. So it's going to form a rectangular region in x, y. Then this is going to allow us to iterate the integrals and call them equal. So we have the double integral over a region of a function f(x, y) dA. This will be the same thing as c to d, a to b, f(x, y). Now, the a to b is the inner layer of this onion. So a's and b's are relating to x, so we're going to do dx on the inside. The c's to d's relate to the y, so the y is on the outside. And then we can also do, we don't have to do x's first, we have to do y's first. And so that's going to give us the integral, so AB is now on the outside, and then CB is on the inside of our function f(x, y). Now the y's are on the inside because we're doing CD first, and then dx. Okay. So I'll draw you a picture, because you guys tend to like those. I think that there should be a market for making baby picture books with like calculus. If they're exposed to it younger, right, it should be easier to learn later in life. So here is your region. So this is not the function, but this is the input space. This is the domain kind of area. So this is a rectangular region is going to look like a rectangle. So suppose we have a rectangle. See, what's funny is some of you chuckled at that, but you'll be the same people complaining in the lab about how to interpret the R, which is just a rectangle. So here's A, here's B. All right, so this tells us my X is restricted between A's and B's, and my Y's are restricted from C to D. Okay, so this is my region R. And we're going to integrate over this region. So recall, I'll do a little recall actually. Yeah, it's a good idea. So recall in Calc 1, when you take this integral, so say you took an integral over something, I'm actually only going to draw the input space. I'm not going to draw a y-axis in a function, because that's not what we're focused on right now. What we would do is we would choose specifically to take a definite integral to find an area under a curve for a specific closed interval. So from A to B, that's what it meant I want the area under the curve from A to B, regardless of what that curve ended up actually being. And so we're interested in the input space, and we'd interpret this input space as this closed interval A to B. Now, our input space isn't just stuck on a line. We can have an X and a Y. And so that's what this rectangle does. It says, okay, so we're doing the same thing. We're integrating across our X's. But on top of that, we also integrate across Y's. And in this doing so, we have A to B, C to D constant. Get a rectangle. Now, there's different ways you could choose to do this. So if I was integrating like this, so the first order, if I was going to do the X's first, and then the Y's second, what I'm basically doing is I'm integrating the X's first across like that, so from A to B. And then after that, I'm going to integrate the outsides secondly with Y's. So then Y's from C to D. That would be the order of integration there. Yes.
So we don't have to concern ourselves with which one we do first.
No, not necessarily. So the context will determine which one you want to do first. Sometimes it'll actually be easier to do one order than the other, but sometimes it's legitimately however you pick and choose. So if it's like a polynomial, well, what do you do? Most times there's going to be the same difficulty both ways. So you just commit to one. Now, this is given in the order of dx, dy. But if I wanted to do dy, dx like this, so doing the y's first, and then the x second, the only thing that changes is the order. So instead of doing what we just did, I would say, okay, well, let me first go from C to D. And then after I've done that for y's, then I'll integrate across my x's from A to B. Notice the directions that I'm drawing these arrows in. It's always from the lower one to the upper one. So the same reason that you don't read this as starting at B and then going backwards to A. Same rule is going to apply here. We're not going to randomly just go from left or right to left here. And then the only thing that we have to consider is for y's, the reason why it goes up is because C is less than B, given by your region. So if you were given, say, R is equal to the points x, y, such that -1 less than or equal to x less than or equal to -1, and 2 less than or equal to y less than or equal to 4, just make sure you know how to do that on your own. Okay, so leave that in your notes. Work on it later. We're going to move on. And then you'll have a chance to do it in your lab as well. Actually, this is the last content lecture before you guys all go to full break. So that's why I'm trying to get these two sections in, so you have something to stew over. Because this is a really, really important mechanic for the rest of the class. The definition, and I know you did this yesterday too, so average value of a function f over some region R is going to be very, very similar to the average formula for Calc 1. The average formula for Calc 1 is simply the distance of your interval, 1 over that distance, and then the regular integral. Now, we don't have just a linear distance, we have a whole area. So we'll just take the area of what a region is, 1 over that, and then it's the same difference. So we'll have the average of our surface, what average surface value we have going on, we divide by the area of our region, our input space, and then just do the double integral. Okay, so that's a quick recap of what you did yesterday. And then in a similar way to how, actually, I'll make a separate thing for this because this is important. Are we good if we erase this? Okay. That's really pretty. I'll keep that up for a second. Sometimes I'll draw things that I wish I didn't have to erase. And then there's some things that I try to erase as fast as possible.
Wait, Scott, I have a question.
Yeah.
So the area is just gonna be from B to A times B to C.
Well,
Or C to D?
yes, except for just flip it around. So A to B, C to D.
Okay.
Yeah. I'm gonna bring a loaf of bread to class if all things go well on Friday, because that loaf of bread will teach you more Calc 3 than I can. Area. Okay, so recall that in Calc 1, if I just took, like, say, the integral, right? From A to B of dx. Wow, exciting, right? So this is basically just telling you how long your interval is. So that'll just come out to be the distance b minus a. Now you can think of that distance along x as the area very loosely. It's not actually an area, but the idea is it's distance of your interval. Well, we do the same exact thing with Calc 3. So now if we have a double integral, so it's a region instead of just stuck on a line, because notice that this is coming from the interval AB because we're restricted to one dimension. Now we're not restricted to one dimension, we have a whole region. Now instead of it being just a dx, we have a little chunk of little bit of area like dA, like little tile, bathroom tile. Okay, raise your hand if you've been in the I4 labs, but in the bathrooms that are right next to the I4 lab, and you see what? And you see all the little tiles in the bathroom. So all those little tiny squares form basically your little dAs. And so the area, the overall area of the basically the floor area of the bathroom is all those little dAs added up. That's what this is. Over some region R, so a bathroom, every single tile is going to sum up to that total floor space area. Okay, so we're doing the same thing. We can imagine this being split up into a bunch of little tiles, like this, and these are little dAs, etc., etc. And as those dAs get smaller and smaller and smaller in area, the precision is going to become infinitesimally precise. Okay, so this is going to actually just be the area of R. So same exact idea. It's analogous concept. The nice thing about this, though, is I'm going to pivot off of this because this is general. This doesn't need to be a rectangular region. Okay, so we don't have to only take integrals on rectangular regions. We can actually integrate over something in our input space that actually has functions defining the parameters of what we're interested in cutting out. So don't freak out. It's not functions on functions and all this crazy stuff. I took about an hour last night to create a very, very nice little visual graphic for you guys to summarize the only possible cases you'll have for the integration orders, okay? So it's not complicated. Just think this all the time in terms of the concept of, I need to do an order of, if I do the x's first, then I do the y's after. If I do the y's first, then I do the x's after. And then just recognize that we don't necessarily have to have this constant value balance, okay? So let's get into that. I'll clear the whole board for this. Okay. Let's see. So first scenario. Here's an input space. X, Y is going to be our other one. X, Y, X, Y. So these are the only three cases for integrating and doing the x's first, essentially. Or wait, no, sorry, the y's first. Yeah, we'll do the y's first. So this is you're going to have some sort of a function with respect to x. So if I have, say, some function down here, and it's like something like that, and this is y is equal to g of x. And if I've got some other function kind of up here, and this is y is equal to h of x. And then notice that they don't have any intersections. And so then the x's are actually going to be bounded by constants. So a. Oh wait, why did I dot that one? So this one's solid, and then dot, b. So do you see what the region looks like? If the region is this So that is not a rectangle. It is a thing. And so, but the idea is we can still integrate just this specific area in our input space underneath our surface. So this is our region R. Now, in the case of doing the y's first, that means we're going to go from the g function to the h function. Why? Because h is taller than g. So we're going to go from here, and we'll first integrate from g to h. And then after doing that, we do the x's after the y's. And so then we'll go across it. So that's case one. Case one, you have two functions that are, one is complete. Don't freak out, it's the national. So the,
So they're controlling
yeah,
our
they did say
phone.
120.
I guess I'm dead.
The government did not choose you, Sam. Okay, let's bring it back. Yeah, probably. Okay. Question for the class: how many intersections are there between G and H? None. Okay. So what do you think the next case is going to be? Yeah, one intersection. So we'll have one intersection between our functions. So
Is it
here
zero intersections?
we're going to have. Well, notice that. So what I mean by no intersections is that G is not intersecting with H.
Oh, okay.
So they're like in this particular interval, they're not the same value.
Got you.
But over here now, it can be possible for them to actually intersect in our interval. So we could have a region that goes something like this.
I think Comcast is going to go up for 30 minutes.
Well, let's remember.
TNT. It's on the way.
B, and this will be.
Is AT&T gone off yet?
No.
Oh, yeah, that was smart.
Yes.
This is
That's awkward.
how many intersections?
One.
Right here. So notice that we might not be given this intersection. So in a problem, practically speaking, you might have to do a little bit of side algebra to find that point of intersection to get that x value, right? So that might not be given to you. Hint, hint, that's probably part of the algorithm you use to solve these kinds of questions. Now, again, the idea is we're doing the y's first. So we're going to do the y's first. We sum from h, g to h, and then after that we go across. H.
Is it because the Y's on top?
Yes, it's because h is taller than g. So we always go from the lower one on the interval to the greater one on the interval. Okay. Good. Then, so this is no intersections. This is one intersection. What's the last case? Two intersections. Okay. So we could have something like, and then so this is our y is g of x, y is g of x, and then our h of x could be something like this. So this is y is equal to h of x. Now we have a point of intersection there. Okay. Have a point of intersection there on the other side of our region, B. So we still have a region in our input space, R, but now it's got these other things. So in this case, it might say, hey, I want you to integrate in the space that is contained, the region contained within these two functions. Then it's completely up to you to find those 2 points of intersection to find what your A and your B is going to be. But the idea is visually, this is really what's happening all the time. Here's a good point. Notice that g of x is actually taller than h of x outside of the interval here. But don't get thrown off by things like that. So whenever you're determining which one is supposed to be the lower one, which one's supposed to be the taller one, only look at your interval a to b. So you're only interested in what you're actually integrating over. So don't make judgment calls about the rest outside of your interval because you're not even integrating over that. So in this context, it looks like h is going to be lower than g outside of our interval, but actually inside of from a to b for our region specifically, this bottom part of the curve is actually coming from g. So we would still integrate G to H, and then across. A to B. Okay. So all three, these are the three scenarios of this. Is when you're asked to take a double integral over some region of a function f(x, y), dA. And the formula you can use, the way you can understand this, is we're doing the x values last, right? We're doing the a to b last, and before we do the x's, we're doing these y's. Now notice that the y's, instead of being equal to a constant, then it says y equals g of x instead of just y equals c. Does that make sense? And then instead of being y equals c to y equals d, now we're to y equals some g, y equals some h. And so instead of putting c and d here, we're going to put g of x here and h of x here. So just because it's a function, though, doesn't mean that we've changed the concept. Concept's still exactly the same as the rectangle. We're just going from the lower part to the upper part. Now that lower part happens to be a function instead of just a flat line, and the upper part happens to be a function instead of just a flat line. But ultimately, that's all we're doing. We're going from the lower to the higher, and this is of our function f x, y. What's the order? So is it dx or dy first?
dy.
Oh, good. Y, and then what's on the outside?
Dx.
Okay. So we feel good about I'm showing you lots of input spaces because I've noticed this is the thing that just kills people. It's not actually the integrals. They just don't know how to set up input spaces because it requires lots of algebra that you kind of have to do on your own. And so there's no procedure for it. So you just need to be aware of what's possible so that when you're given a problem, you can adapt to each individual circumstance. Because even just in the textbook examples, they do a really good job of spreading out all the different kinds of weird things and all the weird combinations of information and clues that they'll give you, and you have to piece together the rest. But so long as you understand, these are really the only three possibilities you're going to have. And if it's one of these, then you can do it in this order with the gx, h is x. Okay, thumbs up, that's good. Because now we're going to switch over to doing the x's first. If we do the x's first, then we're going to actually be having y being a function, or x being a function of y. So that we'll have functions that look like.
Here we go. No, mine's AT&T.
Instead of doing
Yay! I don't feel left out.
it's like, you know, it'd be funny if they did, if the rapture worked where it's like you got a little buzzer and it's just like everybody's phones, you don't go, I'm like, oh, I'm not getting raptured by the government. But I'm not sure I'd want to get raptured by the U.S. government. You just be gone for different reasons. So instead of having functions y equals g of x, right? If we're going to have x's that we're going to be doing first, notice that these are in places of y values. So if we're going to do the x's inside, it's going to be x's as functions of y. So y is going to be kind of like the variable. So the x is g of y, x is h of y, etc. So let's take a look at what those look like real quick. Good to erase?
Yeah.
Cool. Very pretty again. I don't want to erase this one. I can only imagine what the other classrooms in the GC thought last year when I dropped a 15-pound bowling ball right here and it just boom. I'm not going to be redoing that lecture for reasons, but that was a lot of fun last year. If you guys can obtain for me a bowling ball, I might do it.
Oh, I'll get you a bowl.
But I left my bowling balls at home because I knew it was too dangerous for me to have them on campus because I knew I would do it if I had it with me.
You did last year, didn't you?
Yeah, no, because to demonstrate the fields of gravity. Yeah, I did not rehearse that prior to, and so when I dropped it, I didn't realize that there's like hollow boards under here. So it bounced a little bit and reverberated through the entire GC. So anyone underneath probably thought, "Oh Jesus, that's the ball. That's the seventh ball." Yeah. All right. So, anyways, okay.
They have the money to play so.
X1, X1. If you're not drawing these, please start drawing these. X, Y. Okay, so now let's do it the other way. So the first case again, no intersection. So if I have functions of y now, y is the variable, so it'll just be flipped over. So it'll be going like this. So we could have something that looks like this. So this one here is x is g of y, and this one is x is h of y. And then if we can make our region. So it's like a little sail on a boat or something. So the region, you guys see it? It's contained inside of these. No intersections. So this information would have to be given to you. And this is R. All right, so we're going to now be integrating the x's first and then the y's second. So the x's first, we're going to go. For some reason, it's easier to see why we would go from g of y to h of y because we're used to seeing it going from left to right on the x. We're not as used to seeing input values going from low to high on a y-axis. But then after that, we were going to go from C to D. Integrate it out. Note these arrows are giving the directions of kind of if you imagine you're summing up all of the little area chunks that you're doing. It's not actually it's not a vector or something ridiculous like that. Because above this is a surface, right? And this is telling you how you're basically cutting up the pie and then putting the pieces together. So if you think of the surface as like your loaf of bread, the way you're cutting this up as the slices, you're just telling you which order to put the slices up to reconstruct the loaf. I'm just going to give you some volume. So now we can have one intersection. So here's my x is equal to g of y. Then I could have another coming down. And this could be x is h of y. And then close off a region. C, but now we have one intersection, right? So we'd have to solve for that using algebra by setting g of y equal to h of y and solving for which y value that'll occur at. So this is our region. We could have a region that looks like a cute little turnip hat. And we are. So again, this is the case where we're doing x first. So notice that g of y is the one that's closest to the left. So it's smallest x values. So we go left to right, and then after that we go from C to D. Cool. Last case, the double intersection again. So we can have some x of gy, g, and then h of y. So this could be like intersecting parabolas. And so this is x of h of y. And then now, notice we've got our region. And how many intersections? 2. Yeah, so this lower one here is going to be which one, C or D?
C.
And this one's going to be
D.
Good. And then now, even though it looks like we're going from H to G because look, H is less than over here, right? But that's outside of our interval of interest. Our interval of interest is only from C to D. So specifically on C to D, which one is going to be the lesser one? So we're still going from G over. So we do the axis first, and then we go up to D. Okay, so far so good. So note in calculus land, this is what's going on, right? So with the function now, that double integral over that region R. Nice. Why is my handwriting so good with not English? It would be so helpful if it translates itself over. X, Y, A. So you guys actually tell me what's the iterated integral going to look like? What's on the outside?
C to D.
Good. C. Good. So the lesser function of x, and then the greater
F of X.
than the actual surface that we're interested in. Okay, what's the order here?
DX.
You know, I should download the Bob the Builder little sound bite. You know, you can build it. Yeah. You don't need someone to tell you when you're allowed to use common sense.
Can I make a comment about the last one?
Yeah.
So, you know, it looks like the two things he's drawn are functions because it would look like that they would fail the vertical line test. But in this case, we do switch the independent and dependent variables. So we're actually,
So would that be a horizontal line test?
Exactly.
You want to do?
exactly.
Alright.
Or in algebra land. So what you can use is F, right? Now you're taking a Cartesian product of reals, so R cross R, and you're spitting out a single real value, right? That's what fxy does. So that's why inverses are fun, right? Because here we have R2 to R. So R2 and R are not the same set. Now, in the case of high school algebra, what happens is you have F that takes R to R. And so this is regardless of whether or not you want to call the things X in R being mapped to Y in R by the rule F of X gives Y. Because then when you just switch it around, then I say, okay, well, instead of R to R as in codomains, then you look at what the image is of this in here, and you flip the order. And so then it's understood that if Y in R comes from X in R, given under the rule that F of X is assigned to Y, then I can basically take that name tagging system. So it's like when you go to church and drop your kid off, right? You say, oh, my name's Billy Bob Joe, and here's my kid, Billy Bob Sam. And they will put in the computer, okay, so Billy Bob Sam is coming from Billy Bob Joe. And so then you do the inverse process when you go to pick your kid up. They identify, okay, under the rule that you're the parent to the kid, they'll take the kid and they'll undo the process. So you can go the other direction. So you could do F inverse of the kid to match it with the parent. So that's all we're doing here. So that's why so I don't like to think about it in terms of vertical line tests and horizontal line tests, because that oversimplifies the abstraction of what you're doing in a function. You're just simply assigning parent to a kid. And if it's a function, you only have one parent to every single kid.
Or two.
Yeah, no, okay. And then kids can have multiple parents, and so then it expands the idea to relations. And remember when we talked about what equals means? Equals is a function. It's a relation. It's kind of, anyways. So that's why I like the line y equals x. It's a very fundamental object. Are we good to erase this? Okay. I should go on more algebra tangents with you guys. That'd be fun. Maybe I'll make it an extra credit question at the end of an exam. See, because the issue is when people think of functions, they just immediately start thinking about like numerical things and the graphs and stuff. And functions are so much more powerful than what high school chalks it up to be. So there's no need for there to be a mystery when you can just step back and see, oh, you got stuff that goes to stuff. And when you start thinking of a function like that, you're already doing better than most people. So. Okay. Well, that was a lot of pictures. Let's do some integrals now. As they say, you gotta start easy. And as Dr. Lang would say, gotta start hard. And we're gonna do easy first. So let's come up with, let's do a surface. Let's do 4 plus 9 times x squared times 4y squared. And then we need a region to integrate over. So over some region R. You know what's really funny? The calculus part of this is going to be the easiest part for you. The most difficult part is going to be pulling your act together and figuring out what the region is, because you got to remind yourself of all the algebra that you kind of just didn't care about in high school. So use it as use fall break to kind of just, make some flashcards. Do I remember how to graph a parabola from just the equation? Ooh. Do I know how to graph a line from just the equation? Do I know how to graph natural logs, rational functions? Do I know my relations like circles and ellipses? Do I know how to create lines at will to form geometrical sides like triangles in a region? Things that are supposed to be basic that the textbook assumes you know how to do, but do require some practice. So think about that. So let's do -1 to 1 for our x's, and for our y's, let's go 0 to 2. So immediately, what shape is that going to be in our input space? Yeah, because this is just constant. We're bounding x by constant, so we're bounding y by constant. So let's actually draw what this region looks like. I'll just do this. I'll just make like that. My x's and my y's. Okay. X is going between what? Okay. Well, here's -1, here's 1. And what is y going between? Okay, so 0 and 2. So, do you know how to draw this rectangle? Start at the lowest x and lowest y. So lowest x is -1, lowest y is 0. The lowest point. Now we're going to go along the lower boundary and stop at x is equal to 1. And then the highest value is going to be this 2, so that we're allowed to come up to here and to here. 1. So we're taking this little chunk of domain underneath this function 4 plus 9x squared y squared. So this is going to be something up here, and then we're choosing a very specific box to cut out. And I'm trying to think of what would be, ooh, cookie cutters. Okay, so you gotta make cookies, right? You have a cookie cutter. So think of this R as the mold. Okay, so it's not the actual cookie. It's telling you how to cut into. So you spread out your cookie dough, and then you take your cookie cutter, whoosh, right, and stick it in. So that's going to give you the volume of the cookie, specifically with the base shape of the mold. In other words, your region. So your region is your mold. So this is, we're making a square cookie right here. We're taking the dough. So imagine if you did you shaped your cookie dough into a mound that looked like 4 plus 9x squared y squared for absolutely no reason. And so you got cookie dough sticking up off your kitchen counter. And then you drop the square mold down. So that's going to cut out this funny looking thing, but there's all that cookie dough, that's the volume we're after. That's what we're actually doing. Okay, so aside from the fact that I ruined your Christmas cookie making, does it make sense?
Mm-hmm.
Okay. So now that's the hardest part, is understanding why you're doing all of this. Because the easy part is just hand calculating a bunch of integrals. Okay, so the mechanical side of this is not that difficult. It's interpreting why you're doing all of these mechanical things over and over again. That's what's a little bit more tricky. Okay, so let's actually integrate. So we know that, I'm gonna freak all this. Okay, so if I don't have my notes, then I am more assimilated to what it is like to be in your shoes. So then I have to think through more things, and it's gonna be more realistic to the thought process you're gonna have, okay? So we're integrating over a region of a function. with respect to the area differential. And so now we learned earlier that we can basically choose whether I do my a to b first or my c to d first. In this case, integrating with respect to either is going to be just as easy because it's just they're both x squared and y squared, just 10 difference. So let's just collectively choose. Do we want to do x's first or the y's first?
X.
X is first, okay. So if we're doing x's first, then what's going to be on the outside?
Y.
Yeah, the y. So the c value and the d value, I'm not putting in the actual numbers yet. I'm helping you set this up. So then the inside is going to be the x value a to b of whatever your function is. And then we chose to do x's first and then y's. So, yeah. I don't know if you're like me, but the dyslexic side of me really appreciated that when you're handwriting this, the thing that you're doing first is the thing you do last on this side, but then the thing that you're writing here is the thing you do first, and then the thing you do last is actually last. So the way I had to kind of think about it was, you see those, like you go to Walmart, you buy a bag of those tangerines, the little cuties, little oranges. So whatever you choose to be on the outside, that's like the peel, and whatever you choose to do first is like the fruit. Yeah. So double integrals are cuties. You heard it here in calculus 3. See, how many more fun childhood things can I ruin for you in one lecture? We got Christmas cookies, we got tangerines. Okay. I will find a way one day, and it'll be sad for all Nintendo users again. So let's actually plug in what our stuff is. So what's C and what's D?
C.
Yeah, 0 to 2. And then what's A and B?
-1 to 1.
Good. And then fxy is, well, that's just our surface. So 4 plus 9x squared y squared. dx dy. Guess what? If you were that person who just got away with bad notation in Calc 2 and forgetting to include your differentials, welcome to purgatory. So now the gavel has fallen and you'll do penance for your sins and all the time you ignored the dx at the end of your thing. Because it matters now, right? If you just don't include the differential, you look at this and you say, what? What am I doing? And frankly, that's what happens to a lot of people when they forget to do this. So pay attention to all the details. This works together as a whole, okay? So in the same way that when you did a derivative with respect to a certain variable, anything that wasn't that specific variable at that moment, it's just a constant, it's just a number, okay? So we're doing which variable first?
X.
So every single time I see a y in here, that's not an x, so I don't care, it's just a number. So treat it like one. And so what we're gonna have is 0 to 2. What I'm trying to do, also by working through this problem step by step, is model for you the kind of way I want you to be showing your work. Because the way you show your work in these steps is going to govern your accuracy in doing these integrals, especially when it gets longer. I use a hard bracket to denote when I take the antiderivative step. So, antiderivative of the number 4 with respect to the variable is x. It's going to be 4x. Okay. Now, think about this one. What's the variable? Okay, so we're focusing on the x squared part of this. Raise the power. So when you take the integral, we're going to raise the power 1 and divide by the new power. So 9x squared is going to actually just be 3x cubed. All right? So we have 3x cubed, because if I were to differentiate that, that's just 9x squared. And then the constant multiple is just hanging out for the rod. So y squared is unchanged. Okay, is that good? So we just treated y as a constant hanging out for the ride. We do all the rest of it, just calc 1. And then hard brackets to denote that we're evaluating the fundamental theorem of calculus now for x is -1 to x is 1. So we've taken care of the dx's. So what's the only differential that should be on the outside now?
dy.
Yeah. Now, this is another point where people will make silly mistakes. They'll forget what these numbers are representing. Okay, so these are actually the x is equal to -1, x is equal to 1. These are not y values. So don't plug these into the y. Plug these into the x when you evaluate. So if I plug in x is equal to 1 first, I'm going to get 4 plus 3 times y squared minus, and then I got to do the lower bound. So -1 plugged here is -4. Negative, so it's cubed, so it'll stay negative, -3y squared. Notice that I know it's tedious, but I still include good notation. It's dy at the very end. And then now we can simplify. So this is going to be the integral from 0 to 2, 4 minus 4,
8.
3y squared minus 3y squared.
6y squared.
Note my use of parentheses. Whenever you have a linear combination for the integrand, please use parentheses. Because that lets me know that's the integrand, then doing the x, then the y. Here, hard brackets. We took the antiderivative with respect to the x's. Y's are waiting for their turn. This hard brackets to indicate we're still in the fundamental theorem of calculus from the x's. We're plugging in with y's waiting. Now it's y's turn, and here is what they're allowed to do. Okay. Now, that's just calc 1. So in theory, I should be able to just stop here and move on, right? Actually, I'll do that. I'll let you know what the final numerical answer is so you can check your work. But in theory, then from here you say, oh, well, that's easy. That's calc 1, done. But notice how it's conveniently, you should end up with only the other variable left once you've done the other substitution. So because it's 149, I'm going to do the other example, which is equally important for C, which is where instead of it being rectangular, you have to like have fun. You know, it's what's going on.
Bro.
So we want to.
Again.
Ooh, can we miss 10 minutes? That's a question for the game. Ooh. We have options here. Okay, how actually we're going to do this is I'm going to talk through the question. Wait, let me think. Okay, let's do this as a vote. Do you want to spend more time in depth on this on Friday so that we can take like 15 minutes, 20 minutes to go over the full example? Or get the set up now and then just you work on the rest of it on your own?
Friday.
Friday, see the whole entire thing? Okay. So in that case, I'll use these last 10 minutes to get some annoying things out of the way for the class, like announcements. So let's stop this.